All right. Today we've got angle of twist. And we'll go back over torsional stress because we haven't done all of torsional stress. But these two topics are the main parts of torsion. There is one more thing that we'll talk about with power transmission, but we'll do that. I don't know if we'll do that today or not. We might. But mainly torsional stress, angle of twist. You do have. Oh wow! All right. You do have quiz 5 opening. Well, I guess it's open now, but I wouldn't do it until we've done all of the torsion stuff. It's basically about torsion, so it would be tough to do it right now unless you just went ahead and worked ahead on stuff. Lab 2 data should be able to put in the data individually versus uploading some kind of Excel sheet that it looked like you had to do before. So it should be that you can go put your piece of data into lab 2 and then I can compile them all and we can make sense of that. And what else is out here? We're getting close to the end. There's just a few topics left. I guess let's go ahead and start on the torsional stress type stuff. So last time we were working on torsion and we had this equation tau equals T times, and then you either had a rho or a C here. I'll put rho since I did tau instead of tau max. Sometimes you saw it as tau max equals torque times C, and remember C was the outer radius over J. J was the polar moment of inertia, where for us, since we're limiting our torsion to circular cross sections, shafts that are either solid rods or hollow tube type things, then J was always pi over 2, and then C to the 4th minus B to the 4th, where C equaled the outer radius. You have to make sure that you're careful using the radius and not diameter. And then B was the inner radius, and if it was a solid shaft, then B was just 0. Let's see, so we did all of that, and we did a couple of examples with pretty simple things. Let's add in our angle of twist. So this was torsional shear stress, all of this stuff. In fact, let's label it, I guess. So this is torsional shear. It is a shear stress. So you do have to, if you're designing or doing any calculations with factor of safety or anything like that, you do have to use the shear strength to compare with this number of the material that the shaft is made from. It's not a axial like tension or compression, it's a shear. So you do have to use the shear strength. But what this equation will tell us is the shear stress in the shaft at the point wherever we label rho to be. So remember, if you had let's make a circle here. So here's the cross section of our shaft. Rho is measured from the center, so rho equals 0 at the center, and then you measure outward radially, and that distance is rho. And so you can measure or calculate the shear stress at any point in the cross section of the shaft. Normally, you're interested at the very surface, the outer surface. Sometimes you want to know the inner surface. Maybe there's it's a sleeve, so it's a hollow tube that goes over another shaft, and you want to know the shear stress between the two. So in that case, you might want to know the inner surface of the tube. But in general, you're wanting to calculate the maximum shear stress. So that's normally rho equals C, and C is measured from the center all the way out to the outer surface. And that's where maximum shear stress occurs in these torsional problems. So this will tell us about the actual chance, or well, not chance, but the actual stress, shear stress on the rod. So is it going to yield, or is it going to fracture, or anything like that? But it's possible, particularly if this this shaft is pretty long, it's possible that it just twists without yielding even. So it twists, but it doesn't yield. Kind of like if something stretches, but it doesn't leave the elastic region, so it doesn't yield, kind of like a rubber band, but out of metal. It can do the same thing, and sometimes it twists so much that that's a failure. So how we had, remember when we did axial deformation, we had delta, so the change in length equaled P times L, or sometimes I think we actually used the F here, F times L over E times A. We had this relationship to calculate axial changes in length. Well, there's one for torsion that's very similar, theta, so this is angle of twist. And it's in radians, so it'll calculate in radians, not degrees. You can convert it to degrees if you want to, but the equation will give you radians. And it equals, instead of a force causing an axial deformation, you have a torque causing a torsional deformation, or a twist. Still matters how long the shaft is. So a really long, 100-foot long drilling rod or whatever will actually twist quite a bit. It might make an incomplete circle, before the time from one end to the other. So the length does matter. And then instead of E is the modulus of elasticity, and it, you do the tensile test where you pull the part, apply a tensile force, pull it apart, and you put in the slope of the linear part. There's a similar type test where you're twisting, but instead of E, you generate a number called G, and that's called the modulus of rigidity. And you get the same way, you look in, unless you're doing the experiment, you go look up the modulus of rigidity. In fact, it should be in some of these charts. Let's see if I find one. For our, let's see, material properties. Material properties. Oh, I need to tell it to open it. Let's make it a little bigger. So here you've got modulus of rigidity. This first number, first material, I think that's maybe a cast iron or something, wrought iron. It doesn't even have one listed, so some brittle materials don't even list a modulus of rigidity. But other materials have a number here. It is usually, actually it may always be smaller than the modulus of elasticity, around half or so of the modulus of elasticity. And you just grab the number out of the chart. So 11 million for structural steel. Oh, not that. And then TL over J or G. Over here in the axial deformation, we just use the cross-sectional area. In the angle of twist, instead of the cross-sectional area, you use the polar moment of inertia, J. So it's not exactly just using the area, but it's still related to the cross-sectional shape. So TL over JG, or I wrote GJ, will give you in radians the amount of twist from one section, and not necessarily from the end. Whatever length you use in this equation defines the section that you're talking about. So if it's a shaft that has multiple torques on it, then you have to you actually have to do the same type of thing that you did for a bar that had multiple forces on it. You treat each little section separately and add up all the angles of twist. So a super simple example, just so we know exactly what's going on, is shaft that has, I don't know, I think we used 50 Newton meters last time, so let's use that again, although it was too much, wasn't it? So it generated too much stress. So let's make the shaft bigger. Last time we made it 10 millimeters. Let's make it 20 millimeter diameter. But we also now, we have to know the material. So let's call it that structural steel, since we just looked up that number. And we need to know how long the shaft is. So I don't know, let's make it, we're in newtons and meters, let's make it 2 meters long. So it's close to 8 feet long. So it's pretty long, almost an inch diameter shaft, got 50 Newton meters of torque on it. So just to remind ourselves from last time, tau equals T times, or let's do tau max. Tau max equals T times C over J. It does not, the shear stress, torsional shear stress does not care about the length of the shaft. It doesn't care about the material of the shaft. It just cares about how much torque is applied. Technically, remember, that torque is the internal torque, so we ought to cut this guy open and see what's going on the inside of it. And we've got the 50 Newton meters external, and for this little section, this little free body that we cut open to be in equilibrium, I would need 50 Newton meters on the inside. So the internal torque is 50 Newton meters. You wouldn't really have to draw the free body diagram to determine that, but once there are more torques on here, sometimes it does kind of help you to draw the free body diagram of each little section so that you're confident of what the internal torque is. So here we have tau max equals 50 Newton meters. C is the outer radius. I gave it a 20 millimeter diameter, so it has a 10 millimeter radius. My units are meters and millimeters here, so that's not going to work out for me. So I'm going to convert over to meters, let's say. So in order to 1 meter, I'm going to need to divide by 1,000 millimeters to convert those to meters. And then J, it's a solid shaft, so pi over 2. And you can always write c to the fourth minus b to the fourth, like I did over here. But when they're solid, b, the inner radius is 0, so I'm just going to write pi over 2 times c to the fourth, where c is that same 10 millimeters that I'm going to convert over to meters. And then I have to raise it to the fourth power. Be careful to, if you're going to convert and have a power, like raise the fourth power, be sure you do your conversions before doing your exponent, or apply the exponent to your conversion factor also, otherwise you won't be canceling out the right units. If I put the 1 meter over 1,000 outside of the parentheses, if I did this, it's 10 millimeters to the fourth, and then I try to convert it, 1 meter over 1,000 millimeters. This doesn't work because these units would be, well, pi doesn't have units, 2 doesn't have units. Here I would generate millimeters to the fourth, and then I'd multiply times 1 meter over 1,000 millimeters, and the units I'd end up with are meter times millimeter cubed. That doesn't make any sense. So be careful to not make that mistake. All right, get rid of that. All right. So we need to calculate this. Let's see. So we have pi over 2, if we started in the denominator, pi over 2 times 10, but we're going to divide 10 by 1,000. And then we're going to raise that to the fourth. And then we're going to have 50 times 10 divided by 1,000 divided by that denominator. And I get a really big number. Let's see, 318,309,88.62. And the units that get generated here would be newtons per meter squared. So these are pascals. A newton per meter squared is a pascal. And so that's actually not that big, 31.8 megapascals. Do I still have it open? Yeah. So the if this was the structural steel material, the elastic strength, oh, wrong units. Elastic strength in tension is 250 megapascals. This is a shear. Shear is not listed over here. So remember, whenever we don't have a shear listed, we're just going to take half of the tensile strength. So it says still 125 megapascals for the shear strength of this material. So tau, that's the yielding shear strength, 125 megapascals. So therefore, factor of safety against yielding is 125 divided by 31.8. 3.93. So we're plenty safe there. And now what we want to do is we want to see, okay, so it didn't yield, so how much did it twist? If it had yielded, then the axial twist equation doesn't really work anymore, because it would work up until the point of yielding, and at that point, different, it's yielded now, so it has a different modulus of rigidity. Remember the graph, well, here's the modulus of elasticity graph, which will look similar. There's a point somewhere where your slope is no longer linear, and so you enter a region where things don't behave the way that you originally thought they were going to behave. So if we had yielded the thing, then our equation that depended on that modulus of rigidity would no longer work. It would still give us a number, but it wouldn't be the right number. It'd be a way underestimate of what was going on. So our equation for angle of twist is this TL over GJ. So theta equals the internal torque times the length of the section over the modulus of rigidity of the material times the polar moment of inertia for that cross section. So we had 50 Newton meters. We had this section, we said it was 2 meters long. G, the modulus of rigidity, is over in our chart, which I guess, did I close it? No, here it is. Modulus of rigidity for this set of units is this 76, and that's gigapascal, so 10 to the 9th. So 76 times 10 to the 9th pascals, or you may want to write the pascals as newtons per meter squared to make your units more obvious what's going on. And then J is the same thing we had before, except we probably do want it in meters since everything else is over in meters. So, pi over 2 times 10 millimeters converted over to meters, just so that we have consistent units, and then raised to the 4th power. So let's see. And these units should all cancel out. I have newtons per meter squared times times meters now to the 4th, so that gives me Newton meter squared, and I've got Newton meter squared in the numerator, so all the units go away and I'm left with radians. All right, so pi over 2 times 10 divided by 1,000 to the 4th times my modulus of rigidity, 56 times 10 to the 9th, or 76 times 10 to the 9th. 50 times 2 divided by that number, 0 theta equals 0.0838 radians. So if you want to know degrees, because a lot of people don't think in radians, even though radians are the thing that actually relates to the circle versus some arbitrary number of divisions, then you could go 0.0838 radians, and there are, 180 degrees per radian. So multiply times 180. Well, that's over pi radians. So divide by pi. 4.8 degrees. So that's not a tiny amount, but it's not a whole lot. You got a nearly 8-foot long, pretty large diameter, almost an inch diameter steel rod of some kind that has a torque applied to it, and from one end to the other it twists 4.8 degrees. So that's kind of the way that this process is going to work. So on the 4.8 degrees, it doesn't tell you, you have to do these two things at the same time, because the 4.8 degrees by itself doesn't tell you that it's a failure necessarily. That would come from some design constraint on what this rod is supposed to do, if 4.8 degrees is too much or not. The yield stress calculation definitely tells you if that's a failure or not, because it's talking about it would actually deform the material. The 4.8 degrees doesn't tell you that the material is deformed or not. It just tells you that that's how much it should bend. So you almost always have to do both of these calculations. Now, some of the test questions and things like that, it'll just give you a number to calculate, and you don't have to go test unless the problem specifically says so. That it'll twist 30 degrees, but then if you actually calculated the stress, it would have way too much stress in it. Unless a problem specifically tells you to check both of them, then for an academic type problem you're solving, you don't have to check both. But if you're designing something in the real world, then you probably do need to check both of them, because just calculating the angle of twist alone doesn't specifically tell you if that is good or bad. It'll tell you something about a design constraint that you may have established, that this shaft can't twist more than 3 degrees, and then you know that, oh, well, it's going to twist 4.8 degrees. So then you have a problem. But the 3 degrees wasn't anything related to the material or anything like that. It's related to the machine you're designing. So you normally have to do both of these in the real world. Let's see. How about we do one that's just got more torques on it, and maybe different sizes, so you can see how they work together. Let's say that we have a shaft that is stepped down. And we'll put, maybe we'll draw it like that. Let's put our 50 Newton meters on this part. This larger part, let's say that it's having to deal with more than that, 75 Newton meters. And then this other part is connected to something, we don't know what. Maybe it's a motor or a pulley or something like that, but we're not interested in what is connected on that end. So sometimes you'll see them drawn like this, where one end is just connected to something rigid. That's what this thing is modeling. And other times you'll have the problem shown where there's a torque there. So there is a torque there, and we could calculate it just by putting the part in equilibrium, but for now, we'll just do it this way. So we'll label, maybe this is point A, B is right here when it steps down, and C is at the end. And we want to find, so we're given all this, we'll have to be given some other stuff too. Let's see, we're given this is structural steel. We're given, we need some lengths on here. So let's say that this length is 3. I'm still in Newton meters, so let's do meters here. And this one is 4. And what else? We need some diameters. Say diameter of AB is, that one's bigger. Let's make it 0. Well, I was about to write inches. I don't want to have to deal with that. Let's make it 30 millimeters, and the diameter of BC is 20 millimeters. And I think that will get us everything to work on. And what we're trying to find, we want to find the angle of twist from A to C. So from the wall, where it's mounted at the wall, all the way out to point C. This works the same way as when we were doing changes in length, where each time that something in my equation changes, like the torque changes, or the modulus of rigidity, meaning the material changed, or J, the polar moment of inertia, meaning the size of it changed. Anytime one of those things changes, I have to define a new section. So this one would have two different sections. I'd have to calculate the angle of twist in section AB separate from the angle of twist in section BC. So what I would normally do is I would start at the free end and work my way back towards the wall. So I would cut open section BC and draw its little free body diagram. It has the 50 Newton meter torque applied at C, and so the internal torque also has to be 50 Newton meters for that section BC to be in equilibrium. So this is the torque in BC. And then if I'm doing angle of twist, so I'm not doing my stress calculations right now, I'm doing angle of twist. Theta equals, or theta BC equals the torque in BC times the length of BC over the polar moment of inertia of BC times the modulus of rigidity for section BC. So everything has to be specific to section BC. So the torque, the internal torque, there's the 50 Newton meters. The length is 4 meters. The polar moment of inertia is pi over 2. It has a radius, I wrote it down in the given, I didn't write it on the picture, of 20 millimeters, so 20, oh, that's the diameter though, so 10 millimeter radius. And then we'll convert it over to meters. Raised to the 4, so pi over 2 times c to the 4th. And then the modulus of elasticity was that same number, 76 gigapascals. I like using the base units versus converting things to maybe millimeters or whatever. There was, just so you're aware, there was one of the students in the other section, they searched on Google for, let's see if I can find it. They searched, I think, well, convert wow, my keyboard's all crazy. Convert gigapascals to newtons per millimeter squared. All right, they searched for that. And I don't remember what they found. I don't see it right now. Oh, I think it's right here. Something on here, maybe, let's see, 200 gigapascals. No, this did it right, but there was something written, maybe it was in the little summary here. I don't know, somewhere they searched and it told them the wrong conversion, and it basically said that a gigapascal was a Newton per millimeter squared, and I don't see it right now, but it was not correct. So don't always just use the first thing that, oh, you know what, they were using Google to search, not Bing, so that might be a difference for some reason. But it definitely, and I searched it too, and it was a problem. Let's see, because they were trying to do 200 gigapascals to newtons per millimeter square. Well, anyway, Bing really wants to be my search engine, apparently. All right. Anyway, be careful on using online converters, because I looked at what they saw, and it said that a gigapascal was a Newton per millimeter square, which is not. A megapascal is, but it was not doing the right thing. So anyway, back to, I just like writing all the base units in my equation and doing it myself. All right, so let's see what this number is. Let's see. Gotta plug all these numbers in. All right, if I did it right, I get 0.1675, and again, these are radians. So times 180 over pi, 9.6 degrees. That's a lot, but it is 4 meters long. So, and it's the same size as the one we just had. So that kind of, I suppose, should just be twice what we just had. So that makes sense. One thing on this, remember, it's hard to tell if these internal torques are clockwise or counterclockwise because it depends on which way you're looking at them. So you have to pick one of the signs to be positive. So when you're drawing these things, you have to say, is this a positive internal torque or a negative internal torque? I'm going to say that these are positive. Why it matters is it's possible that you have one of these shafts with a whole bunch of torques on it, and some sections have an internal torque that's going one direction, and other sections have an internal torque that's going the opposite direction of that. And so you have to keep track of positive and negative angles of twist. The same thing as when we had the axial deformation, and some sections were stretching and some sections were compressing, and you had to keep the difference. Obviously, it's easier to see if something's stretching or compression, but here you do have to assign something to one of these. So I'm going to assign this shape arrow as positive. So this will be a positive angle of twist. And then I would go, so that's just from section, or from point B to C. That's the amount of the 10 degrees here, the 9.6 degrees here is just that piece. But section AB is also twisting, so I need to go in there, cut that one open, and see what's going on inside it. So it has the 50 Newton meters at C, and then at B, we added another 75 Newton meters. Both of those external ones are going the same way. So they add together and create an internal torque that has to balance those of 75 plus 50, 125 Newton meters. So this section is going to have a larger internal torque, but it's also a larger diameter and it's shorter, so it may have less twist on it. But I do see that this internal torque and this internal torque are both going the same direction, so they'll add together. All right, so the angle of twist, this would be from section AB, from point A to point B, and the torque is going to be the torque in that section, the length of that section, the polar moment of inertia of that section, and modulus of rigidity for that section. So the torque in there we just found was the 125 Newton meters. The length, I'm pretty sure it was 3 meters, yes. It also had a larger diameter. I gave it a 30 millimeter diameter, so it's going to have 15 millimeter radius. Same material though, so it has the same 76 gigapascal modulus of rigidity. All right, so I get 0.062 radians, or times 180 over pi, 3.56 degrees. And I'm okay with that number. It is a much higher torque, 50 compared to 125 in this section, but it's a shorter piece and it's got a much larger diameter, or a good bit larger diameter. So I'm okay with a slightly smaller angle of twist. And then what I do is the angle of twist from A to C equals the angle of twist from A to B plus the angle of twist from B to C. In this case, both of those are positive, or what I assign to be positive. They're both the same sign. Whether they're both negative or both positive doesn't matter. So AB was the 9.6 degrees and BC was the 3.56 degrees. And I just add them together. So 9.6 plus 3.56. Wow, I multiplied them. 9.6 plus 3.56. 13.16. And so that would be the total angle of twist from, can't get it all in there, from the wall at A all the way out to C. And so this would be kind of a, I don't know, a mid-level problem for exam 3. Not terribly hard, but there's a couple of steps, a couple of places you might go wrong on calculating it. So it's not a super easy one. This one's pretty on the easy side. So this would be the one of those first few problems where it's one step really, and not a whole lot to it. All right, any questions to this point? All right, so let's talk about one other thing. So most of the time, not all the time, but a lot of the time, these shafts are used to transmit power. Oops, that should be an S. So they're rotating, you know, they're connected to a motor on one end or a pulley or a gear or something that's making them turn, and then they are in, you know, down the line in the machine somewhere, they are making some other piece turn. So they're transmitting power from one place to another. We're going to take a pretty simple approach to this power transmission. We're going to assume that power is conserved. If we do want to take into account the idea that there are losses in our system, which there would be, you're not going to have 100% power transmission from your motor over to whatever it's driving. But we'll just say that the machine or the system is some percent efficient. Like it might be 80% efficient or whatever. And so if you put in 100 horsepower, then you get 80 horsepower out. And so we'll just kind of keep it pretty simple that way. And we'll assume that our elements like gears and pulleys and all that kind of stuff are not, they're not slipping or anything like that. If we have a loss in power, it's to the, it's just kind of this generic thing that's kind of happening in the whole system to cause losses in our system. So there's heat being generated and things that are slipping and all that, but we don't care exactly what is happening to cause the power loss. We'll just say that there's some percent loss of power, and we'll deal with it that way. I think we'll start with just 100% efficient systems and not worry about power loss. But we do need to try and figure out how to calculate power. So we're going to use power equals, let's write it out instead of just variables. Power equals torque. So kind of the same torque over here, 50 Newton meters, 75 Newton meters, whatever torque is being transmitted in that little piece of the puzzle, times how fast you're transmitting it. Now, in this case, we're going to call that speed. Our speed, well, I want to write it this way, is going to be angular velocity. And so a lot of times we're going to use power equals torque times omega. Omega is going to be angular velocity, T is going to be torque, and P is going to be power. And we'll have units of something like horsepower, probably not a capital P. Or we'll have hertz. A hertz, not a hertz, that's a speed. We'll have watts. And those are, I guess we could have just the base units of like inch-pounds per second. You know, we could have something like that, Newton meter per second, or a joule per second. You know, all of those could be the units. A lot of times you're going to obviously calculate numbers and they'll come out in something like inch-pounds per second. But a lot of times you need to convert them over into either horsepower or watts, depending on if you're using the US system, you convert to horsepower, or if you're using the SI system and you convert to watts or kilowatts or something like that. But the equations are going to want things like inch-pounds per second and Newton meters per second. So let's see, let's say that we have a motor, and we'll just have some kind of, maybe it's a 5 horsepower motor, and it is spinning at, I don't know what speed, we'll make it 80 RPM. So 5 horsepower motor spinning at 80 RPM. It's got this little output shaft that's connected to something. We don't know what, but let's say that this shaft has a diameter of, now we're back over in the US system, so let's make it 1/2 inch diameter. And we'll make it our generic little structural steel material. Okay, so we got all this stuff. And maybe we want to find, well, we don't know the torque here. We know the speed, we know the horsepower, we know something about the size of the shaft and the material shaft. Let's say that we find the tau max in the shaft and factor of safety against yield. All right, so we want to find those things to see if this shaft is going to, this 1/2 inch structural steel shaft is up to the task of dealing with whatever this motor is doing. All right, so we have power equals torque times omega. Now you have to, most of these little power transmission problems involve a lot of figuring out how to get what you know into the units that will work in the equations, because, you know, if I take power equals torque times omega and I put 5 horsepower equals torque times 80 RPMs, if I do some unit analysis on that, that's not going to generate any kind of useful units. So the one thing I'm going to need to do first is I need to know how to put 5 horsepower in the equation. I can't just put 5 horsepower. So I have to convert it over to something that looks more like inch-pounds per second, maybe foot-pounds per second if I wanted to deal in foot-pounds, but inch-pounds per second is normally what I do. So horsepower really does go way back into the times when machines were starting to do the work that horses were originally doing, horses and mules and all, you know, ox and that kind of stuff. So people knew about roughly like, oh, a horse can move this and do that, and it can go this fast and all that kind of stuff. And so I don't actually know the experiment that was done, but there were types of experiments of walking horses around in circles at certain radiuses, certain speeds, and all this kind of stuff to lift weights and all that kind of stuff. Anyway, they came up with the idea that 1 horse, so 1 horsepower, can generate about 550 foot-pounds per second power. And so you could think of this like if a horse was connected to some kind of cable system that had a 550-pound weight on it, he could lift that weight a foot per second. So that kind of thing. Now normally foot per second or foot-pounds are not the units you want in your equation, because you might have other things that are going to be in inches instead of feet. So it's easy enough to convert this over to 6,600 inch-pounds per second. Just multiply it by 12. 550 times 12, unless I'm doing it wrong, should be 6,600. Yes, 6,600. So that conversion factor is the one you just have to know, kind of like inches to centimeters and stuff like that. You just have to know how to get a horsepower over into inches per second, and it's just memorize it. All right, so if I have 5 of these, I have 5 horsepower times 1 horsepower, horsepower is, I'm going to use the inch-pounds per second, 6,600 inch-pounds per second. So that will get me over to, 40,000 inch-pounds per second or whatever it is. All right. So let's move that over. Equals torque. We don't know the torque. It told us the speed. So we can actually use this calculator or this equation to calculate the amount of torque. We do know the speed, but again, this speed is given in RPM. So RPM equals a revolution per minute. And, that's a kind of universal speed, but it does occur more often in the US units. You'll see Hertz, HZ. You'll see Hertz more often in the SI type system when you're talking about speed. You might think of Hertz as like something to do with electricity, which it also is. A Hertz is actually a generic thing that just means a cycle. In this case, the cycle is revolution. Instead of per minute, it's per second. So cycle per second of any kind of cycle, whether it's some kind of oscillating current type thing in an electricity setting, then it could be Hertz in that sense, or it could be a shaft that's spinning around at some speed per second. So cycles per second, RPM, revolutions per minute, or cycles per minute. So I don't want revolutions per minute in this thing. What I actually want is radians per second. So in my equation, power equals torque times omega, I want radians per second. So I got to convert my revolutions per minute over to radians per second. So revolutions per minute. The minutes, well, there's 1 minute has 60 seconds. So now I'm in revolutions per second. So basically I'm in Hertz right now. And then the revolutions, so that's 1 360-degree revolution, but I don't want degrees, I want radians. So 2 pi radians in 1 revolution, and now I'm left with didn't want to do that. Radians per second. So if I take, and it looks like 2 pi over 60, multiply that times my RPM, I'll convert to radians per second. So I had 80 RPM times 2 pi over 60. I guess that's radians per second per RPM. I'll have radians per second. All of that to get to a value for torque. So if I use this equation, let's see, I've got 5 times 6,600. So on the left-hand side, I have 33,000. That would be inch-pounds per second equals torque times 80 times 2 times pi divided by 60. 8.378. That set of units will be radians per second. When I divide them through, the seconds will cancel out and I'll be left with inch-pounds. The radians are still, there, but they don't affect the torque. So the torque is equal to 33,000 divided by this 8.378 number, and I get 3,938.9 inch-pounds. Okay, what I really wanted to know was the maximum shear stress in the shaft and the factor of safety against yielding. So here's the torque. Now I can go to tau max equals T times C over J. T is the torque I just found, 3938.9, that's inch-pounds, times C. I said this was a 1/2 inch diameter, so the radius is a 1/4 of an inch. J pi over 2. I didn't say anything about it being a hollow shaft. I didn't draw it hollow or anything like that, so it must be a solid shaft. So 0.25 inches to the 4th. And so the units on this should work out to be pounds per square inch, which is what I would expect for a shear stress to be. So 3938 times 0.25, the radius, divided by pi over 2, divided by 0.25 to the 4th. Oh wow, too much. 160.5 KSI. If I go and look up my material properties, I'm in the US units again. Structural steel doesn't have a shear strength listed, but so when they don't have a shear strength, then I just take half of the tensile. So 18 KSI, I had 100 and something, 160 KSI, so we have a problem. Factor of safety is our tau, we did yielding, over tau actual. So our yield strength was 18 KSI. Our actual stress was 160.5 KSI. That is 18 divided by 160.5, 0.112, which is not good. If we did everything correctly, then our 1/2 inch diameter shaft spinning at 80 RPMs trying to deliver 5 horsepower won't make it. It just can't do it. So we would have to slow it down quite a bit, make it bigger, or transmit less horsepower, or make it out of different material. I guess we ought to make sure that we did everything right too. I didn't ever check it. 80 times 2 times. That seems right. Oh, no, that was right. I did do that. Let's see. 5 to the 4th times 2. Oh, yeah. I think it's just not a good scenario for our little shaft that we built here. All right. So what we should do is sometimes you'll see these problems as design problems where one of these pieces of information is missing. Here the torque is missing, but it's not really. We just calculate it. But it might be that maybe we don't know at all the diameter and we need to figure out the diameter. In this case, the diameter would have to be pretty large to support the torque that we're trying to deal with. But we could do that. We could leave the diameter as a variable in here and say that we know tau max, tau allowable basically would have to be like 9 KSI to have a factor of safety of 2 against the shear stress, and calculate the necessary diameter, which would end up being pretty big. All right, we'll do more of these power transmission. We have to talk about some gear ratio things because a lot of times these power transmitting devices are, so for instance, this one, maybe you need the 80 RPMs as your output, but it's not going to work to just hook it straight up to the motor. Maybe you've got to spin the motor a lot slower and then gear it up later so that the output is actually 80 RPMs, but the motor's only spinning at like 5 RPMs or something. So maybe that would be one way to solve it. So next time, Monday, we'll talk about how do you deal with the gear trains. That's where your losses are going to come in, or one place, a big place where your losses are going to come in. Again, we're not going to worry too much about power losses, but we're just getting started on it. So you should be able to do some basic power transmission calculations, some pretty, you should be able to do all the angle of twist calculations, assuming that we actually stay in the plastic or elastic region of our material. And you should be able to do shear stress calculations for parts that are in torsion. Any questions about stuff? Good. All right. I think there are, upload your data to the lab 2 so I can go ahead and compile that. Make sure you get those DXF files in for the truss. If you send one in, you might send me an email because I don't necessarily see it. It doesn't like pop up and tell me that you submitted one. And as soon as you send them, we'll go ahead and cut them versus waiting until the 8th to cut them out. So if you do send one early, then let me know.